So let's look at learning and then forgetting and then learning again. And this is a description in an artificial neural network. So the network learns two subsets of associations. So that puts, or let's go down here a bit. So x1 acting on w0, the weight vector is going to be d1, so it gets all the stuff in A1 correct, and similarly it gets all the stuff in A2 correct. Any input given by the columns of matrix x2 gives you the right output in terms of an entry of the vector d2. So after learning both bits, the weight vector is some w, call it w0. The second stage is that there will be forgetting of A1 and A2. And by forgetting, this is just partial forgetting. It needn't be forgetting everything, but not everything will be remembered. So that changes the weight vector, changes the state of the artificial neural network. And so now we look at x1 acting on w1 minus d1, that is non-zero. So we look at its squared length and think of that as the squared error. And now we relearn A2, but the only A2. We don't bother to relearn A1. We hope that that will come back free. So the weight vector is now a W2. And this is done by projecting W1 that we've got by forgetting onto A2, orthogonal projection. I will show you some pictures very shortly. And so now the squared error after partial relearning is x1 w2 minus d1 length squared. So we're going to compare these two squared lengths. And we're going to hope that after relearning we are closer to knowing everything on A1. We're hoping that this one at the bottom is less than that one there in the middle. So after forgetting everything, the squared error is x1 acting on w1 minus d1 squared. After relearning, the squared error is x1 acting on w2 minus d1 squared length. So the amount of free lunch learning is this difference of squared lengths. The distance, squared distance after forgetting minus the squared distance after relearning. And we would like this to be positive. This thing delta is positive if and only if relearning A2 brings W closer to A1. So let's have an example. N, the big space, is going to be 2. N1 is 1 and N2 is 1. So let us start with this line. So we're in two-dimensional space. This is the space where the weight vectors live. And here is L1 that tells us about the associations A1. So if we learn the vocabulary for A1, we know that W lies in that line. And if we learn associations A2, we know that W lies in that line L2. And if we've learnt both bits, then we must be at that point W0. Now the next stage is forgetting. So we were at W0, but we forgot something, and by forgetting, the weight vector changes to something else, W1, let's say there. And the way it does it is it moves along some vector v. And you can see in this picture that here is the distance in the dashed blue line, that's the distance of W1 from lying in L1. And now I think we're going to relearn. Yes. So from W1, the next thing we do is we relearn all the associations A2. In my example, that was animal words. And we do it by going from W1 down to L1, the space corresponding, L2 corresponding to A2. We come down by that blue arrow. It's the orthogonal projection. And so here we were, we started off at W0, where we remembered all the associations. We'd learnt both L1 and L2. Then we forgot. The weight vector moved to W1. Then we relearnt A2. We projected down by that solid arrow and we got to the point W2. And the question is W1 closer to L1 than W2? No, it isn't. By relearning and going to W2, we're closer to this line than we were after we had forgotten. So in this example, the squared distance for W1 is bigger than the squared distance for W2. There is free lunch learning. I have drawn for you just one picture. I could have drawn another picture, and if I started by forgetting and the forgetting vector went somewhere else, then it could be that delta, the amount of free lunch learning, the difference in squared lengths, would be negative. Here it's positive. Okay, so we can play around with the amount of forgetting. We can play around with where W1 goes. Now you'll see that there's bits, well, there are bits of a circle around here, and some of them I've put in red. And the red bits are, well, if V points towards the red arc, then there is free lunch learning. Delta is positive. If V is out here and doesn't point towards a red bit, then there is not free lunch learning. So in this picture, you'll see that the amount of red round the circle is big. It's bigger than the amount of black. And that means that the probability of free lunch learning is positive. Now, of course, the only thing I've allowed here to be random is V. It's a random vector. Later, I shall allow both these lines to be random. So, let's think about how forgetting might occur. Forgetting involves moving the weight vector from W0 to W1, and we've done it by moving through a vector V. Under the kind of forgetting called synaptic drift, V is random and it's isotropic. In other words, any direction is as likely as any other direction. So the probability of getting V is the same as the probability of getting some rotated version of V. So if U is an orthogonal matrix, a rotation matrix, the distribution of U acting on V is the same as that of V.